Assalamualaikum warahmatullahi wabarakatuh. We are on the second part, conservation of momentum. So this is quite similar to conservation of energy. Okay, conservation of energy. So energy is conserved. Here, conservation of momentum means momentum, total momentum is conserved. So when a system is isolated means only those two or only one. Okay, so you would find that the amount of momentum, it doesn't change. Okay, so the effect that it doesn't change, for instance, for example given in this picture. Alright, this is trying to show the concept of propulsion. So a squid, when it's emitting or squid water or propelling water in one direction, due to the conservation of momentum, the squid itself will be propelled in the opposite direction. Why? Okay, because of the conservation of momentum. Okay, let's approach the scenario by the concept first. Okay, and then later on we verify the concept, yeah, in saying that it will move in the opposite direction. Alright, so in the situation whereby we have two objects collide with one another, okay, or perhaps touching one another, in contact with one another, and therefore there is a contact force involved. So we find the equation would be something like this, whereby force exerted on one body would be equivalent to the other body exerted on the other body. Okay, Newton's third law. We are talking about Newton's third law over here. So basically, we find as well that due to the concept of Newton's law, the amount of force is equivalent to one another, and of course because they are contact with one another, and definitely we arrive with the force is the time frames or time is the same. All right, and we arrive with the expression of course change of the momentum, and by right, okay, remember the Newton's third law that I did mention earlier. Okay, so rewriting it becomes the concept of impulse is equivalent to one another. It's just that the amount of force now is the same, yet in the opposite direction, Newton's third law. Okay, and because of that, the two expression that we seen over here, okay, the two expression is now going to be embedded into the coming expression of the impulse and considering Newton's third law. Okay, so how it's gonna looks like, you're going to see the expression turns into something like this. So earlier F and then delta T, and then again negative F and delta T. So this negative is over here, and of course you have 1, 2, and then even 2, 1 over here. Okay, so nama. And this expression, okay, if you find it quite confusing, you can have this as V, this as U. And again, here as V, here as U. Rearrangement of this expression gonna get you the V final over here. Arrangement of the V final, right? Sorry. You can have it the other way around, no problem at all. All the V final are now in one part, or the momentum final in one part as equivalent to the momentum initial in one part of oppositely. So this result you the product of what we call total momentum initial is equivalent to the total momentum final, where we call this as conservation of momentum. Come. Alright, so conservation of momentum, very simple. Total momentum is constant, or total momentum initial equivalent to total momentum final, provided no net external force X on a system. So there's no net force. Okay, there are forces, but when they are added up, the resultant force is equivalent to 0. So this is considered as isolated as well, as such. Now, so let's try to apply this concept with this example. And in this example, we are going to see that original system is one object, and then this object later on gets separated. Okay, so what is the situation? We have an archer. So archer, basically you can imagine that he's gonna have his arrow, and his quiver. Okay, so to provide a situation there's no external force, we find that there's no friction, so friction gonna be on ice. Okay, so he stand on ice to get frictions disregarded, so his total mass including his bow quiver is 60 kilogram. So originally everything is 60 kilogram. And then B question, get his recoil velocity. Okay, if he fires 0.03, okay, take notes of the term recoil. All of a sudden people they're gonna use recoil. Why? So he fire means he gets separated from not moving, now start moving with an arrow leaving him at 50 meter per second in positive x direction. Try to imagine in front of you, yeah, or even to your right. Now, next is, so how do we go with this question? Okay, so you're gonna see that he's originally not moving at all. No, nobody is moving. So that's how you arrive with total momentum originally to become 0. But right after that, he would be moving because his arrow is now as well moving. So in this case, you find in the situation final over here is that get separated into two. One meant for the arrow and another meant for him, or even the archer lah. Archer together with his what quiver earlier. Okay, whatever left of him lah. So mass of the arrow itself, mass of the arrow is 0. Sorry, okay, so in the equation they have it the other way around. So this is meant for the arrow while this is the archer. Okay, never mind, as long as you get it right. Okay, so the mass of the arrow itself is 0.03 and the velocity is 50 moving to the right. Okay, that's how you substitute. Mass of the man, okay, he is 60 with everything. But now what happened is the arrow is leaving him. So of course you have to minus whichever left out lah, yang kena buang lah arrow dia. And that's why the mass 1 now turns to be only 59.97. You have to minus with the arrow. Okay, so with this mass, okay, he is going in the opposite direction. So that's why the term is called recoil, because the effect that the arrow move in to the right, he would be moving in the opposite direction. That's recoil. Okay, we'll try. Okay, basically we're not going to discuss B and C because it's going to involve, or even D, involve 2 dimension. We're going to keep it simple to only 1 dimension. That's all folks. Looking forward for our next video.